Hi guys, please like, share and subscribe and contact this number if you want full lectures of any CM or CS subjects. Thank you. Okay, so the next distribution that we have got is called as the gamma distribution. Okay, it is represented as x follows gamma with parameters alpha and lambda. There are two parameters alpha and lambda. Now what is it? What does it model? It is basically the sum of alpha IID exponential lambda distributions. Okay, so you have independent and identically distributed exponential lambda distribution x1 x2 all the way up till x alpha. So there are a total of alpha such exponential distributions which all have a parameter of lambda. Okay, and their sum follows the gamma distribution. So if x is the sum of x1 to x alpha, then x will have a gamma distribution. Okay, in real life what this can be thought of is if you see in case of exponential distribution, I told you that exponential distribution models the waiting time of a particular process that happens at a constant rate. The process is a Poisson process. Okay, so for example, a car is coming at a signal that will the waiting time, the time you have to wait for a particular car to come, or for example you are waiting at a bus stop, the time you will have to wait for a bus to come when you after you reach the bus stop has an exponential distribution. Okay, so now if you are waiting for 10 such buses, okay, if you are waiting for 10 such buses, the total waiting time for 10 such buses will have a gamma 10 comma lambda distribution if the buses are coming at a rate of lambda. Okay, so this is basically a sum of 10 exponential lambda distributions. Okay, so that's fairly straightforward to understand. Okay, this is a sum of exponential distributions which are independent of each other. Okay, and they are identically distributed. All of them have the same exponential lambda distribution. Now if you see what is the PDF of this, so PDF in the tables is given as this expression. I'll not get into the derivation of this. It is lambda to the power of alpha upon gamma alpha. This gamma alpha is the gamma function. I am going to talk about it in a bit. Okay, x to the power of alpha minus 1 e to the power of minus lambda x. Okay, where x is greater than 0. So this is your PDF. Okay, let's talk about the gamma function in a bit, but this is your PDF. Okay, what do I mean by gamma alpha? I'll clarify on that. Okay, what is the expectation and the variance of this distribution? Of course, expectation would be alpha times the expectation of the exponential lambda distribution. So alpha into 1 upon lambda, that is alpha by lambda, and the variance will be alpha upon lambda square, because alpha into the variance of the exponential lambda distribution, that is 1 upon lambda square, so it just becomes alpha upon lambda square. The derivation of these two I'll just do right now. Okay, so the two things that I'll discuss now are the gamma function and the derivation of the expectation and the variance of the gamma distribution. Okay, so let's move on with that. Okay, so we just discussed that your PDF for the gamma distribution is given by this function, that is fxx is equal to lambda to the power of alpha upon gamma alpha into x to the power of alpha minus 1 into e to the power of minus lambda x, right, where x is greater than 0. Okay, so this is your expression for the PDF. Now I use the gamma function here, which is gamma of alpha. So what is this gamma function? The rules relating to the gamma function or the description of the gamma function is given on page 5 of the actuarial tables. Gamma of x is given as all of these rules are given there. You can go check them, so you don't need to learn anything here. The gamma of x is basically integrating from 0 to infinity t to the power of x minus 1 e to the power of minus t dt, where t is the variable of integration, where x is greater than 0. Okay, so gamma of x is given by this expression. Okay, it can also be represented as x minus 1 factorial. So gamma of x is same as x minus 1 factorial. For example, if I ask you what is gamma of 5, so gamma of 5 will be same as 4 factorial. Okay, this is true for all values of x that are greater than 0. Okay, next you have got here is gamma x is equal to x minus 1 into x minus 2 factorial. Now this is quite obvious because we know that gamma of x is equal to x minus 1 factorial, which can be written as x minus 1 into x minus 2 factorial, which can be written as x minus 1 into gamma of x minus 1, because x minus 2 factorial is same as gamma of x minus 1. Okay, by this rule directly, if gamma of x is gamma or x minus 1 factorial, then x minus 2 factorial can be written as gamma of x minus 1. And this is one special rule that applies: gamma of half is equal to root over pi. So these are 4 rules that you need to know, okay, in order to use the gamma function. I have given you the definition, 2 alternative definitions of the gamma function, and I have given you the definition of gamma half, which is root over pi. Okay, now next thing is I'll just get into the derivation of the expectation and the variance of the gamma distribution. Okay, so deriving the expectation first. Expectation of x is just integrating over the entire range x into fxx dx, which will be equal to integrating from 0 to infinity x into lambda to the power of alpha upon gamma alpha into x to the power of alpha minus 1 into e to the power of minus lambda x dx. Right, now if you see, what happens here is, taking from 0 to infinity, this just becomes, here you have got, let's just take this lambda to the power of alpha upon gamma alpha outside. Okay, let's just do that. Inside you just have got x to the power of alpha and e to the power of minus lambda x dx. Now notice one thing: if this thing you want to make it a complete PDF of the gamma distribution, in order to make it 1, you need to do some sort of adjustment here. See, in the original PDF you usually had x to the power of alpha minus 1, and along with that you had this these two alpha terms, which are lambda to the power of alpha upon gamma alpha. Now this power of x has changed, it has become alpha. Now it's no more alpha minus 1, it is alpha now. So now in order to make it a PDF, what you need here is, you need terms like alpha lambda to the power of alpha plus 1, because instead of alpha minus 1 you have got alpha now in the power of x. So the power of lambda, instead of alpha it would just be 1 more, because this is 1 more than this, so this has to also increase. So it will just become lambda to the power of alpha plus 1 upon gamma of alpha plus 1. Okay, so these two adjustments are needed. So if you will multiply this term, you will also have to divide by this term. So you also need this term here. So I'll just multiply with the reciprocal of it, gamma of alpha plus 1 upon lambda to the power of alpha plus 1. Okay, this sort of adjustment can be done in order to make this a complete PDF. Okay, which should make sense, which is what we have done for all the other distributions as well. So what do you have here? So gamma of alpha plus 1 upon gamma alpha, this is just, if you see logically, this is what, this is your alpha factorial, and this is alpha minus 1 factorial. Okay, so these two will cancel out, it will just become alpha in the numerator, and in the denominator you have a lambda. So it is just alpha upon lambda, and inside you just have integrating from 0 to infinity lambda to the power of alpha plus 1 upon gamma alpha plus 1, okay, e to the power of minus lambda x and x to the power of alpha dx. Now if you will see this, this is nothing but the PDF of gamma alpha plus 1 comma lambda distribution. Okay, this is the PDF of gamma alpha plus 1 comma lambda distribution. Okay, so your expectation finally becomes alpha upon lambda. Okay, that's your expectation, right? Because this entire thing, PDF integrated over the entire range, just becomes 1. So you're just left with alpha upon lambda. Similarly for the variance. Let's see what happens in case of the variance. So expectation of x square can be calculated very similarly. I'll apply the same procedure very fast. 0 to infinity x square into um, lambda to the power of alpha upon gamma alpha e to the power of minus lambda x and x to the power of alpha minus 1 dx. So this time this will just become 0 to infinity, lambda to the power of alpha and gamma alpha will come outside, and you will have e to the power of minus lambda x and x to the power of alpha plus 1. So now that you have an alpha plus 1 term here, what you need is you need a lambda to the power of alpha plus 2, because this has to be 2 more than this, 1 more than this. So if it is x to the power of alpha minus 1, it is lambda to the power of alpha, right? If it is x to the power of alpha plus 1, it just becomes lambda to the power of alpha plus 2, okay, upon gamma of alpha plus 2, and these need to be uh, if you multiply you need to divide as well, so it just becomes gamma of alpha plus 2 upon lambda to the power of alpha plus 2. So this entire thing is just the PDF of a gamma alpha plus 2 comma lambda distribution integrated over the entire range just becomes 1, and the remaining part is just, you'll see it is alpha plus 1 into alpha upon lambda square. That's what remains. This is expectation of x square. So variance of x just becomes expectation of x square minus expectation of x whole squared, which is nothing but alpha plus 1 into alpha upon lambda square minus, this is what alpha upon lambda we have already seen, okay, this is alpha upon lambda whole square, okay, expectation of x whole square. Now just to simplify this, you can take alpha by lambda square common, okay, inside you will just have alpha plus 1 upon lambda square, okay, no, alpha plus 1 minus alpha, okay, so it will just alpha and alpha will cancel out and your variance becomes alpha upon lambda square. Okay, that's your variance. So that's how you find the mean and the variance. Now let's move on to the probabilities of the gamma distribution. Okay, also remember one connection between the gamma distribution and the exponential distribution. Exponential distribution is just a gamma 1 comma lambda distribution is equal to an exponential lambda distribution, okay, because it is already a sum of alpha exponential distribution. So if you take just one exponential distribution, that will be gamma 1 comma lambda distribution, okay. So this is one thing that you should remember. Now I will just move on to the to calculating the probabilities of the gamma distribution. Okay, so this is a book question. It says x follows gamma 2 comma 1.5 distribution. Calculate the probability that x is greater than 4. Now there are two methods of doing it. I'll just go to the more obvious method first, and then I'll get into the method which is to be discussed after that. One thing to note here is you do not need to learn any PDFs or anything. These are pretty complicated PDFs, so like you should know how they come, what is their significance, what is their application, where they can be applied. But honestly, you do not need to know about where you do not need to learn them, because they are all given in tables, okay, as we have seen before as well. Okay, so now let's get into the calculation of probability that x is greater than 4. How do I calculate that? So greater than 4 means integrating from 4 to infinity, okay. The PDF will be what is the PDF? Lambda to the power of alpha upon gamma alpha e to the power of minus lambda x upon into x to the power of alpha minus 1 dx, right? This is your PDF. Now putting in the values, going from 4 to infinity, lambda to the power of alpha just becomes, I'll just take these two terms outside, okay. Lambda to the power of alpha becomes 1.5 squared upon gamma alpha, okay. What is gamma alpha? It's gamma of 2. Okay, that's it. And e to the power of minus lambda x, e to the power of minus 1.5x, and x to the power of alpha minus 1. So x to the power of 1 dx. Right, that is what you will have. Now how do you solve this? Okay, again this is integration by parts. Okay, if I apply the rule properly, if you want to solve this is pretty simple. Using integration by parts, you just have to apply it once. Okay, so by applying the rule ILATE, which one comes first? Okay, so algebraic, this one should be taken as the first term, this is the second term. Okay, so now let's just calculate the probability. 1.5 square upon gamma of 2. Okay, here you'll just integrating these two, x as it is, e to the power of minus 1.5 x upon minus 1.5 minus integral of the derivative of this and the integral of this. So I'll have to integrate this twice. So this just becomes e to the power of minus 1.5 x upon 1.5 squared. Right, that's what it will become, integrating from 4 to infinity. Right, now honest, let's just check this. So if you will check this, it's very easy. At infinity, both of these terms will become 0, right? Because e to the power of minus infinity is 0. When you'll put infinity, these will be e to the power minus infinity. At 4, they will take a value. So let's write that value. That is just 1.5 square upon gamma of 2. This one will be 4 into e to the power of minus 1.5 into 4. Okay, this is negative because this is the second term. Okay, upon minus 1.5. Okay, again this one will be positive. Negative is positive. E to the power of minus 1.5 into 4 upon 1.5 to the power of 2. Okay, so that's how you just have to apply simple integration by parts. Okay, and the answer will be, okay, so the answer comes out to be 0.0174. Here all the answers are to be given, the final answers are to be given up to 3 significant figures. In CM1, the number of significant figures in CM1 and CM2 happen to be 5, and in case of CS1 and CS2, you should give the answers up to 3 significant figures. Okay, so that's something to remember here. Here they don't want to check your accuracy, they want to check your aptitude basically. Okay, the question solving ability. Okay, so right, so let's move on, next thing now. Okay, so now one important thing to appreciate here is the fact that we could solve this question, the question we just solved, because the value of alpha was sufficiently small. See, if you'll see, alpha minus 1 goes in the power of x here. Okay, and here since alpha was 2, we had x to the power of 1, right? Now if you had x to the power of 2 instead of 1, then you would have to apply integration by parts twice. Okay, if you would have x to the power of 3, then you will have to apply integration by parts thrice. Okay, so as the power of x increases, the number of times you'll have to again and again solve this using integration by parts just increases. Okay, once you'll apply integration by parts, you'll differentiate this value of x, then you'll have one lower power, and then keep on, so on and so forth. So what if alpha is equal to 20, alpha is equal to 30? Then you won't be able to apply integration by parts directly, right? It just becomes very difficult. Okay, so that is why instead of this method of integrating actually to find this probability that we just found out, instead of this, what we do is we go for another method which goes through the chi-square distribution. Okay, now what is the chi-square distribution? Chi-square distribution is a special case for gamma distribution. Basically, if you have gamma nu by 2 comma half distribution, that is, you replace alpha with nu by 2 and you replace lambda with half, okay, then that is the equivalent of chi-square nu distribution. Nu here is the Greek letter nu, which represents the degrees of freedom. We'll discuss what are the degrees of freedom in a later chapter the exact definition of degrees of freedom, but for now you can just think of it as the parameter of the chi-square distribution, okay, and it is represented by the Greek letter nu. So if you have gamma nu by 2 comma half distribution with these parameters, then that is the equivalent of, that is the same as chi-square nu distribution. So these two are exactly the same things, okay, and that is your definition for chi-square nu distribution. Another definition you will find eventually is that we'll learn the normal distribution eventually, okay, and when you will see the normal distribution, you will find out that chi-square distribution is just the square of the normal distribution. So if x follows a standard normal distribution with parameters 0 and 1, we'll talk about what this means, you will understand the significance of this later, then x square follows a chi-square 1 distribution with 1 degree of freedom, okay. So that is also a relation, there is also a relationship between normal distribution and the chi-square distribution, but that comes later. For now it is just a form of gamma distribution, okay. Another relationship, that another way this relationship can be expressed between gamma distribution and chi-square distribution, both of these ways of relationship, they are written in the tables, okay, you don't need to remember again, the relationships are already given for you to help you find the probability. The another way for this relationship is when x follows gamma distribution, gamma alpha comma lambda distribution, okay, then 2 lambda x, if I multiply this with 2 lambda, will have a chi-square alpha by 2 distribution, okay, I'm sorry, chi-square 2 alpha distribution. We have seen that nu is equal to 2 alpha here, right? Nu is equal to 2 alpha. So it will have a chi-square 2 alpha distribution. So if x follows a gamma alpha comma lambda distribution, if you multiply this x with 2 lambda, then that will follow a chi-square distribution with degrees of freedom as 2 alpha, okay. This definition can be used to derive any probability for the gamma distribution, okay, because the probabilities of the chi-square distribution are already given in the tables. So now I'll just give you a few questions as to how do we find out the probabilities of the gamma distribution. So let's move on to that. Okay, let's look at a couple of questions from the book itself, and 3 of these are from the book and 1 I have just given by myself, okay. So x follows a chi-square 5 distribution, that's what they're saying, and they are asking us to find probability that x is greater than 6.5 and probability that x is less than 11.5. So these two are to be found. These are directly chi-square probabilities, and in the other two questions I have given gamma distributions where you have to find probabilities. So first let's just try to find the probabilities of the chi-square distribution directly, and then we'll look at how to convert gamma into chi-square and find the probability, okay. So chi-square first. So probability x is greater than 6.5. Okay, so probability x is greater than 6.5 where x has a chi-square distribution with 5 degrees of freedom, right? That was the number of degrees of freedom? Yeah. Okay, perfect. So how does that work for me? So if you will see this, see here these probabilities are given in the tables. So if you will go to the tables, I'll just switch to the tables. These are the actuarial tables, and this is page number 164 for you, okay, 164. So 164, on page number 164 of the tables you will find these probabilities, and if you see this diagram here up here, these are the CDF of the chi-square distribution given. Let's if you see x here, okay, on the graph, the left hand side is shaded, so less than probabilities are given. All the probabilities given down here are less than probabilities, okay, and if you want to find the greater than probabilities, then you'll have to do 1 minus the less than probabilities. Fine. So now you have to go for chi-square 5, right? Chi-square 5. So chi-square 5 is right here, and in this, which probability do you want to find? 6.5, greater than 6.5, right? So 6.5 chi-square 5, the value is 0.7394, but this is the less than probability, so the greater than probability would be 1 minus 0.7394. Okay, what is the other part? I'll write the answer of both of them together only. So this is how it works. Okay, the other part is less than 11.5. Okay, so probability x is less than 11.5. Okay, so here 11.5 value is also given, 0.9577. This can be found out directly. Okay, so this is how you solve this, and this value will actually come out to be equal to, if you'll see the answer for this, this one comes out to be equal to 0.2606. okay, and this is 0. Okay, no, this was 11.5. This is fine. There's one more, probability x is less than 11.8. Now what do you do in this case? Okay, now here 11.8 value will not be there. Okay, you have 11.5, you have 12, so you'll need to interpolate. So let's see how do we interpolate. 11.5, the value is 0.978, no, 0.9577, and 12 value is 0.9652. okay, so probability x is less than 12 is equal to 0.9652. Now I'm going to teach you how to interpolate. Okay, that's one important trick which comes in very handy in this subject. If you know how to do it, you can skip this part. Okay, anyway, so I'm going to do that. So at value 11.5, your value is 0.9577. okay, at value 12, your value is, against value 12, x is equal to this, and this is your CDF value. Okay, that you want to find out, less than probability 0.9652. and what you want here is you want the value against 11.8. so now I'll teach you a technique to interpolate here. How do you interpolate without learning a formula? Usually people will make you learn the formula, but I don't believe in cramming formulas, so I'll just tell you how to do it. Okay, so the point here is that you need to find this value which is in the middle of these two. This is basically 0.3 ahead of this, and the total distance here, if you see, from 11 to 5 to 12 is 0.5. okay, so basically you want to go 3 steps ahead out of the total 5 steps on the total gap of these two. Okay, so how do I find this value? The probability that x is less than 11.8, you obviously know that this value will be greater than this because this CDF is in increasing function. Okay, so between these two, it will be an increase, it will be between these two, and it will be greater than the lower value, so it will be greater than 0.9577. so I take 0.9577 plus. Okay, plus what? Okay, plus I want to take 3 steps out of total 5 steps, so 0.3 upon 0.5. I want to take 3 steps out of total of 5 steps. On what gap? On this total gap between these two. Okay, so if this gap represents 5 steps, I just want to go ahead by 3 steps. So 0.9652 minus 0.9577. Right. So if this is the total distance, okay, you are trying to find the value between this value and this value here. So you just want to go 3 steps out of a total 5 steps on this total gap between them, right? If total gap is 5 steps, you are just taking a proportion of 3 by 5 on that. And that's how you interpolate. So this will give you your answer for probability x is less than 11.8. Okay, let's see. So your value becomes 0.9622. So you don't need to learn the formula for interpolation ever. You can just make it out of common sense. So this is just common sense, taking 3 by 5 of the total gap and adding it to the initial values. So from the initial value, go 3 steps out of a total of 5 steps on the total gap. Okay, so that's how it works. Okay, now let's just move on. Okay, now let's just look at the gamma distribution cases. So x follows gamma 2 comma 1.5 distribution. This we have done before, and find the probability that x is greater than 4. So we know that if x follows gamma distribution with parameters alpha and lambda, then 2 lambda x has a chi-square distribution with degrees of freedom 2 alpha. And this is the definition that I am going to use. So what do I want to find? I want to find probability that x is greater than 4. Okay, so what I need to do is, in order to modify this into a chi-square distribution, this x has a gamma 2 comma 15 distribution. I need to multiply it with 2 lambda on both sides. So probability that 2 lambda x will have a will be greater than 2 into lambda into 4. Okay, what is the value of lambda? Lambda is 1.5. So probability that now 2 lambda x, the distribution is chi square 2 alpha. So chi square 2 alpha, what is alpha? Alpha is 2, chi square 4. Okay, is greater than 2 into lambda into 4. Lambda is 1.5. So 3 into 4, 12. This is the probability that I need to find out. Now this is greater than. I can convert it into less than because the table only has less than probability. So chi square 4 is less than 12. Right. Once you have this, you can just find this out from the tables. Okay. So let's just go to the tables. Chi square 4, and I have to search for the, so degrees of freedom new, I check for 4. Last time I checked for 5, this time I check for 4. So in this 4, now x, the value is 12. 12 is 0.9826. Okay, this is the less than probability. So 1 minus 0.9826. So this just becomes, the answer comes out to be 0.0174, which was the answer we had found earlier with integration. So this is just an easier method to do the same thing. And this is another case for gamma 10 comma 20. Now in this case you cannot do it by integrating at all. So what you need to do is, you need to apply the chi-square distribution. You have no other option. Okay, you cannot integrate from 7 to 0 to 7, because if you'll integrate, you'll have x to the power of 9 alpha minus 1, where you'll have to integrate 9 times at least. So that's not feasible. So you'll have to do it directly. So probability that x is less than 7 can be found out as probability that 2 lambda x. Okay, instead of 20, let's change this a bit. Let's make it 4. Okay, gamma 10 comma 4. Okay, so 2 lambda x. So 2 into lambda x will have a chi square 2 alpha distribution. So chi square 2 alpha will be chi square 20 distribution, and this is to be less than 2 lambda x is what I have to multiply. So 2 into lambda, lambda is 4, 2s are 8, 8 7s are 56. So chi square 20 is less than 56. This probability is what I have to find out. Let's go here. So chi square 1 to 14 is here. I have to go for chi square 20, right? Chi square 20 is here, and I have to check the value 56. So beyond 50, it just, okay. So beyond 50, it is just almost equal to 1. Okay, in 20 list, if you'll see, it is just almost 1. So your answer becomes almost 1 only. So chi square 20 is less than 56 is just 1. Okay, so that's your answer. Okay, and that is how it works. Okay, now let's just move on.